Okay, Assalamualaikum. It's still me, Dr. Shaiman. So we have now reached at the last subchapter. Okay, still under the chapter 4, unbalanced fault analysis. So this subchapter is very important because it talks about the single line to ground, line to line, and double line to ground fault. Okay, so I hope you can give a full concentration. And I think it's not that difficult, so I hope you can cope with that. So without further ado, let's go. Okay, let's go. Right. So it's unbalanced for analysis. So single line to ground. So I'm going to start with the single line to ground. Okay. So most of the fault occurs in power system are unsymmetrical fault, which result in unbalanced current flow. So it can be analyzed by using the method of symmetrical components. Okay, we are going to use the symmetrical components that we had learned before to determine the fault currents. Okay, for current and voltage of the system after the occurrences of the fault. So basically, they have three major types. One is single line to ground, also we call as SLG. Second one is the line to ground, so we call it sometimes LL. And third one is double line to ground, or we call that as DLG. Okay, these all three faults are very common for the unbalanced fault. Okay, so first of all, for the case of single line to ground fault, so another generator with single line to ground fault. So this is the figure, example of figure. So basically, you're going to have the three phases, so which is phase A, phase B, and phase C. So for the case of single line to ground, the clue is means that one line is grounded. For this case, the A line or the A phase is grounded. Okay, so the A phase is grounded. So when the A phase is grounded, ground mean zero now. That's why VA equal to zero. So for this case, VA equal to zero. Okay, VA equal to zero. So VA equal to zero means short circuit. Okay, VA equal to zero. While the other two, IB and IC equal zero. Okay, so VA equals 0 and IB and IC, these both are equal to 0. So this is the condition of the single line to ground. But remember, we have this neutral reactance. Okay, we have neutral reactance with the Zn here. Okay, neutral reactance or impedance. Okay, so this is the IA flowing from here and separated. Okay. So basically for the equation that will be used in fault analysis is about this equation. So this equation. So from this matrix. So VA0, which is zero sequence for the VA. So and then the VA1 and VA2. So equal to 0 VA and because B1 positive sequence we have the remember positive sequence we have the generator. On generator only placed at the positive sequence only. While no generator at the zero sequence and the negative sequence. So minus Z0, Z1, Z2, IA0, IA1, IA2. This is the basic equation for single line to ground. Okay. Then basically symmetrical components of currents can be found from, so I think you still remember the symmetrical components are very important here. It's the same means that we are going to find the symmetrical components. That's why we derive it from the IA, IB, IC. But for this case, because the IB and IC equal to 0, that's why this part is equal to 0. Means IB and IC equal to 0. So it's the same equation on the previous chapter. Okay. And then what's next? So from here, we can easily calculate which is the IA0 equal to IA1 equal to IA2 equal to IA over 3. So IA over 3. Okay. So basically we get IA0 equal to IA over 3. Where when we replace the value, so means that the IA over 3, so we just replace the value of IA1, okay, IA1 into the previous equation. So this equation we put into here. So we replace all the value here with the IA1. Okay, it's now become IA1, 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 all are IA1. Okay, then from here, okay, from this matrix, okay, matrix, oops, from this matrix, then we can easily get BA0 equal to minus IA1 Z0, BA1 EA minus IA1 Z1, BA2 equal to minus IA1 Z2, where we know already the phase current for the A, okay, the phase voltage for the A is equal to positive sequence plus negative sequence plus zero sequence. So then we just replace substitute the value, okay, which is equal to EA minus IA1 Z1 minus IA1 Z2 minus IA1 Z0. Okay. So, however, for this case, VA equal to 0. So VA equal to 0 means that so this VA equal to 0. That's why it become like EA equal to IA1 multiplied with Z1 plus Z2 plus Z0, where the IA1 is the EA over Z1, Z2, and Z0. So this is the equation. So this is the important equation that we have here. So again, when we're going to find the IA, so we try to find the IA. So IA0, IA1, and IA3 equal to IA. But it means that IA, so IA is the okay, IA is the sum of the IA0, IA1, and IA2, so which is equal to 3 multiplied with IA1. Okay. Okay, for example, we have this kind of thing. So this is how you withdraw the equivalent circuit for the case of single line to ground. So for the case of in the previous subchapter, so we separate the drawing about positive sequence, negative sequence, and also the zero sequence. But when we do the fault, for this case it's single line to ground, so we are going to include all these three in one equivalent circuit. So this is how it looks. Okay, this is how it looks. So basically this is Z1. So Z1 means this part is the positive sequence. Okay, positive sequence, and this is Z2. So this is the negative sequence. Okay, coming from the negative sequence. And this is ZG0, ZG0 till Zn, which is these two are same with the Z0, which is the zero sequence. So all these three sequences will be combined in one equivalent circuit. Okay. So let's go for the example. Okay, the example 150 MVA 13.8 kilovolt. Okay, by connected synchronous generator has a synchronous negative and zero sequence reactance 50%, 10%, and 5%. Okay, so the neutral of the generator is solidly ground. So neutral of the generator is solidly grounded, which is the single line to ground. Generator is connected to short transmission line with positive and negative sequence reactance of 10%. It's connected to short transmission line with positive and negative sequence. And there's the impedance of 30%, which is the okay. And then what else? Okay. The generator was unloaded with single line to ground fault because on phase at the end of the line. We find the fault current. The point is to find the fault current and the voltage at fault line at the generator terminals. Okay. So if we look at the diagram, so the diagram of that question. So they have the generator. They have the three types of value. So, sorry, this is x1. So the positive sequence for the generator 1. Okay, let's put generator 1. Is x1 0.2, negative sequence 0.2, and zero sequence is 0.05, which is based on the question. Yeah. Okay. Yeah, 20%, 10%, and 5%. Okay. Then they have the line. So with the line is x1 equal to x2 equal to 0.10, which is the positive, and C1 is 0.1, which is here. And generator is connected to short transmission line with positive and negative sequence. The positive is 10%, positive and negative are 10%, while the zero sequence is 10%. That's why 0.1, 0.1 and 0.3. Okay, next, what should we do? How to draw it? Okay, we are going to draw as they become like this. Become like this. Okay, you see, we separate it into two, which is let's say we put this one as the terminal, and we put here as terminal. So we separate it into two parts. So the generator part is here. So we put basically this one, we have the generator as one plus, so positive sequence, negative sequence, and zero sequence. Where this is 0.2, this is 0.1, and this is 0.05. Okay, and then we're going to have the line. So the line have 0.1 for both positive and negative. So 0.1 here, 0.1 here. And remember, because x1, they give you the value of x1, that's why only j. Okay, but they give you the z. Without the j means that one only for the resistance only. But for this case, basically, generator everything is all about the reactance. So that's why they write in x. So that's why this one j is coming in. Okay, here they don't write because the reactance itself equal to j. Okay, complex. Then we get j 0.1, j 0.1, and for the case of this one, j 0.3. So basically, we have drawn already the chemistry for the single line to ground. Okay, positive, negative, and sequence. So when we get this, of course, this is the IA1, and this IA2, and this is IA0, which is same like that, IA0. Okay. Okay, then what should we do? Because we need to find the IA1. Our target is to find the IA1 because the equation given is the IA1. Okay, or positive sequence, current of positive sequence. Okay, so we just use the equation that already derived before. So we just use it. Okay, here the EA. Okay, the EA. Since the EA, they don't mention any value of the EA. That's why same case with the power flow solution. If you still remember the power flow analysis, the log flow. So when you don't have the value, so we assume it initial value for the EA of voltage is 1.0 and the phase is 0. So it's very basic. So we just substitute the value and then put the Z1, Z1, Z2, Z0. So this one is the Z1 total, and Z2, and this is the Z0. So that's why 0.3, 0.2 plus 0.35. Then you just don't forget the J because it's all about the reactance. Okay, the reactance. Okay, that's why don't forget J. Then phase 0 over J multiplied with 0.85. Then you got 1.176 with the phase of minus 90 degree or minus J 1.176. This one is the complex number. This one is the phase angle. Okay, phase angle. Then we get the IA1. Then after that, as we mentioned, we understood already for the case of single line to ground, IA1 equal to IA2 equal to IA0. That's why 1.176 with the phase of 90 minus 90 degree is all same for the three sequence. Okay, positive, negative, and zero sequence. Then after that, then we're going to get the IA. Same, we refer from the equation that we learned before. So IA equal to 3 IA1, which is IA1 also same with IA2 but IA0. But it's okay, we just put the positive one is more positive. So this one multiply 3 multiply with IA1, then we get this value. Okay, this value. Fine. Means that it's a different expression using the matrix. So this one we have the IA, IB, and IC. Okay. Then we get after we get the IA0, mean we get the zero sequence, positive sequence, and negative sequence of the IA. Then we can calculate for the case of B and C. B and C. Okay. Just substitute. But as we already mentioned before, apparently IB already zero already. IB and C already zero, so same value like before. Okay, it's the same thing. It's the same thing with this. Okay. Alright, so finally, when we got all the value for the current at point F, okay. So I base at the 4 is, if you still remember now how to calculate the I base, what is this? What is this? This is the MVA FM, okay, which is for this case is 150 MVA. So this is the value lah. Why this one is the BL, if to remember, or line voltage, okay, which is the 13.8 volt based on the value we have. So 13.8 volt multiply with the root 3, then we get 6276 amps. This one for the I base, not the for current yet, okay, at the phase current, okay. So then after that we get the IA because we just multiply with the I base. So basically this is the per unit area, so this is in per unit, and then we just multiply it, then we get 22,140 or 20.14 kVA.